to the deep dive. Today we're diving into a core piece of how a ton of the web actually runs smoothly. It's all about JavaScript and, how it manages to get so much done even though it's single-threaded. It's like a one-lane road where theoretically only one car can pass at a time, but somehow it manages to keep traffic flowing.
Yep, exactly. You've probably heard that JavaScript is single-threaded, and at first that might make you think, well, how can that possibly be efficient? I mean, you see all these dynamic websites, these super responsive applications, and Node.js powering all this stuff in the background, all running on JavaScript. So the question is, how on earth does it handle all of that without getting completely bogged down? That's what we're going to try to unpack today.
Exactly. And a big part of the answer lies in something called the event loop. You can think of it as the behind-the-scenes traffic controller, making sure everything moves smoothly without causing any pileups. We're going to break down what that means, looking at the actual technical docs that lay out how JavaScript behaves at its core at runtime. We'll demystify all of it and give you a real sense of how web apps, especially modern ones, and those Node.js environments, how they stay responsive, how they just work, without getting bogged down in jargon.
And look, this isn't just some obscure theoretical computer science concept. Understanding this stuff, understanding the event loop, has real benefits. When you're out there building websites working with server-side JavaScript, the way the event loop works directly impacts how you should design your code. If you get it, you can write code that's more performant, create applications that feel smoother, and just, well, work better.
Right, so first things first, let's clarify this whole single-threaded business. Imagine you have, say, a single chef in a kitchen. They can only work on one dish, one task at a time. Right. Now, if they have to wait for something, let's say a stew needs to simmer for hours, well, they're kind of stuck. They can't just move on to the next order while that's happening, and the whole kitchen slows down.
It's the same with JavaScript. These kinds of waiting tasks, they're what we call blocking operations. Think of things like waiting for a server to send back data or dealing with a massive file. If JavaScript just sat there and waited, everything would freeze up. In a web browser, imagine that. You click a button and nothing happens. An animation stutters and stops. It'd be a terrible experience.
Yeah, exactly. So that's where asynchronicity comes into play.
Yeah.
We need a way for JavaScript to kick off these tasks that might take a while and then go do something else without waiting for them to finish. And then somehow it needs to know when those tasks are done so it can pick up where it left off.
And that's where our hero, the event loop, steps in. It's like that super efficient system our chef might use to manage a ton of orders without getting overwhelmed. Instead of just standing there watching a pot, the event loop is constantly checking if anything's finished. And it lets the code know when it's time to come back to a certain task.
Yeah, it's like having a whole bunch of timers and sensors, and when one goes off, the event loop says, hey, this thing is ready, go deal with it now. And that's what keeps everything moving. The documentation we have actually calls it a constant cycle of checking for events and executing their associated callbacks. It's the core of what makes something like Node.js so efficient, how it handles so many connections at once without needing a dedicated thread for each one. Pretty elegant solution when you think about it.
Absolutely. So this process of watching and reacting, it's not random. It's super organized. The event loop goes through very specific phases, each with its own job. The event-loop-js.pdf document breaks it all down really well.
Okay, so let's walk through those phases one by one. Where do we start?
Well, first up is the timers phase. This is where those callbacks you set up with set timeout and set interval, that's where they get executed. For instance, if you had code like set timeout console.log timer 1 0, even though you've technically set a delay of 0 milliseconds, the actual execution of that callback, that console.log timer 1, happens during this timers phase. Might not be instant, but it'll get there.
Gotcha. So after timers, what's next on the list?
Next, you have the pending callbacks phase. This one handles callbacks that are waiting for certain system-level things to finish up. Like if you have a TCP connection and there's an error, or maybe some specific I/O operation needs to wrap up, those callbacks are dealt with here. Let's say your application's trying to read data from a file, but there's a permission issue. The callback to handle that error, that would likely happen during this pending callbacks phase, right? So your app can figure out what to do, maybe log an error message or let the user know something went wrong.
Okay, so that's timers and pending callbacks. What's next?
Next up is a quick one. It's the idle prepare phase. The document mentions this as mostly internal to Node.js. It's all about getting the system ready for the next loop iteration. You can think of it as like taking a quick breather to reset and prepare for the next wave of tasks.
Okay, so we're at the idle prepare phase. What comes after that?
Now we're getting to the heart of the event loop. This is the poll phase. And it's a big one. This is where most of the input and output operations are handled. Think about your app reading from a database, making an API call to fetch data, or receiving data over the network. All of that happens here. What's interesting is that if there's no I/O stuff happening right at this moment, the event loop will actually pause here. It waits. If it finds finished I/O operations, it executes their callbacks. But if there's nothing to do, it just chills out and waits for something new to come in.
That's really interesting. So it's not just constantly running in circles. It actually knows how to chill out and wait for the right moment to jump back in.
Exactly. And that's a big part of why Node.js is so good at managing a ton of connections without using up a ton of resources. It's not just spinning its wheels, it waits intelligently. This is a big takeaway, especially if you're thinking about building systems that need to scale really well.
Makes sense. So we've got timers, pending callbacks, idle prepare, and the all-important pull phase. What else is there?
Right. After the pull phase, we have the check phase. This is where callbacks scheduled using setImmediate are executed. You might think this is similar to set timeout with a zero delay, but there is a slight difference in terms of exactly when they're executed in relation to the pull phase.
Okay, interesting. I'm guessing there's just one more phase left, right?
You got it. Last but not least, we've got the close callbacks phase. This is for callbacks that need to run when certain resources are closed. Imagine you have a network socket, and it gets closed. You might have a callback attached to that event using something like socket.onClose. Or maybe you're closing a file descriptor. Those callbacks are run here during this phase, letting you do any necessary cleanup or final actions.
So we've got this whole cycle of phases, checking for tasks and executing them in a specific order. But then there are some tasks that sort of jump the queue. They get VIP treatment. I'm talking about process.nextTick, callbacks, and those associated with promise resolutions. These are often called microtasks. In the document, they call this a special case, and it seems like it's for a pretty good reason.
Right, you hit the nail on the head. Understanding these microtasks, that's really key here. So with process.nextTick, those callbacks and the ones tied to resolved promises, they actually get executed between each phase of the event loop. And here's the kicker. All of those queued up microtasks will be fully processed before the event loop moves on to the next phase. They're like the high priority express lane.
I'm starting to see why that would be important. So if I understand correctly, it's like having a separate inbox for urgent stuff that you clear out completely before even looking at your regular mail.
Exactly. And that's why, in the example code they provide, things might seem a bit out of order at first glance. Remember this code JavaScript .setTimeout, console.log 0, setImmediate, console.log immediate, process.nextTick, console.log nextTick, console.log nextTick, promise.result. Now console.log start.
Yeah, I remember that. Looking at it, you'd think the timeout, even with zero delay, would fire first, but it doesn't.
Exactly. So let's break down why. That very first line, console.log, that runs right away. It's part of the main synchronous code that's running. But then, before the event loop even gets to its first phase, all of those process.nextTick callbacks get their turn. That's why you see nextTick printed out second.
So the next tick jumps ahead of everything else because of this microtask priority.
Got it. Right. And then comes the promise. Remember, even though it's an asynchronous operation, when a promise resolves, that then callback, that's also treated as a microtask, so it gets to cut the line too. And since all microtasks are processed before the event loop moves on, you get promise logged out right after nextTick.
Makes sense. But what about those last two, the set timeout and set immediate? They seem a bit trickier.
Okay, so here's how it works. That set timeout callback, it gets added to the timers queue, and the set immediate callback goes into the check queue. Now, because of the way the event loop is set up, because of how it checks timers at the very beginning of a new loop, and then how that interacts with the pull phase, you often see the set timeout callback running before the set immediate one. It's subtle, but that's why you end up with timeout being logged before immediate.
So the order start, nextTick, promise, timeout, then immediate. It all comes down to this priority system for microtasks, and then the specific way the event loop goes through its phases.
Precisely. And, you know, if we zoom out and think about the bigger picture of asynchronous JavaScript, these underlying mechanics, the event loop with its phases and those special queues for microtasks, that's what makes those higher level asynchronous patterns, those things like callbacks, promises, and async await, that's what makes them all work.
Right. Those are the tools we use as developers to manage this asynchronous world. But under the hood, the event loop, that's the engine that's making it all happen.
Exactly. And it's all about keeping that main JavaScript thread from getting blocked. It's essential for making sure our applications stay responsive.
So to really hammer home the key points, I guess the first one is JavaScript, even though it's single-threaded, it can handle so much because it's built on this event-driven asynchronous architecture. And the heart of that is the event loop.
Absolutely. And the event loop, it's not just some vague process, it's a very structured cycle of phases. Each one handles specific types of tasks. If you can understand those phases, especially that pull phase and how it waits for and then processes I/O, you have a much better grasp of how things actually work under the hood.
And then there's that special priority given to those microtasks, those things created by process.nextTake, and promises. That's really important to make sure certain asynchronous operations are taken care of as soon as possible.
It's all about responsiveness, right? And this isn't just theory. It has huge practical implications. Whether you're writing code or just trying to understand how these technologies work, understanding the event loop helps you see why certain coding patterns are better for handling things like network requests or file operations. It's how you avoid creating those bottlenecks that lead to your applications becoming slow and unresponsive.
So as we wrap up this deep dive into the JavaScript event loop, remember that this is the thing, the engine that keeps the wheels turning. It's constantly cycling through its phases, managing all those asynchronous tasks, making sure our web applications and Node.js environments stay smooth and responsive.
It's the key to efficiency and responsiveness in modern JavaScript.
And that's it for this deep dive. I hope you all enjoyed it. But before we go, I have one last thought for you to chew on. Given that JavaScript has this single-threaded, event-driven design, that it relies so heavily on the event loop, think about this. How does that architecture impact the choices developers make when they're building those really big, complex applications? How does knowing this change your understanding of responsiveness and efficiency in software? Mull that over, and we'll see you next time on The Deep Dive.